No, that's, thank you. And the next presentation from Jace from Japan. Reza will be presenting, right? It's about geolocation techniques for detecting unknown radiometers. You know how to use it. So, right? Yeah, you can press the button.
Okay, good afternoon, everyone. Thank you for coming for my presentations. My name is Reza. I'm coming from JICE, Japan Advanced Institute Science and Technology. I'm also with Institute Technology Sumatra in Indonesia, Sumatra Island. I am welcoming you to come to know me city in JICE and also in Sumatra Island. And also, that also I'm here. You can help me to answer questions. Okay, my presentation about the DRSS was based the differential receives signal strength based photograph for geolocation and position detections of the unknown radio emitter. The emphasis of unknown. Unknown means like illegal radio. Sometimes we don't know the transmit power or the departure of time, something like that. It's confusing. So my outline is motivation and basic structure, formula derivation and simulation and conclusions. Okay, the motivation of the wireless geolocations. Yeah, the wireless geolocation has been used for a long time ago. For example, for the aviation, for the planes, for the aeroplanes. And about 40 years ago, GPS started to be issued, but still not so booming. And also the commercial of GPS also still a few decades ago. So after the FCC, Federation Communications Commissions in America, USA, give the issues the requirement to apply E911 in every wireless communication. That's the wireless geolocations become booming until now. Also for 5G and healthcare, to tracking the old people, the elderly people, the young people, or needy people. Agricultures, for example, for harvesting, to know to locate the epidemic of disease of the plant, or intelligent transportation, for navigation of the car, and mobile station positionings, for the 5G, also location sensitivity, and many others applications such as the wireless charging. Also using the beam forming, using the localizations to know the position of the device want to be charged. But our focus is in unknown radio emitter. So in unknown radio emitter, for example, is we do for disasters, for example, any radio communications that's still active. After disasters, we can search victims. Also, in, for example, illegal radio. For example, this is in Tokyo 2020. This project also sponsored by Code and Electronic. This is also to support the Olympic 2020, for example, for the monitoring radio, for example, for jamming the broadcast of the Olympic and something else. So why we use photographs in our research? Photograph is a bit graph. This is has several advantages. For example, utilizing the stochastic properties. In this case, it's using mean and variance. And by using the mean and variance, also we reduce the complexity of the processings, and also with factor graph, this factor graph can factor the global function to the local function from complex to simple. And then the utilization of the stochastic properties is done by the sum product algorithm. By sum product algorithm, we compute the marginal various marginalizations. And then with factor graph, it's very easy to understand the algorithm, to observe the behavior of the messages, so we can improve the algorithm or make the new algorithm, or we can improve the specific function inside the global function to improve the technique. And then this is the basic structures of the factor graph base that we in our research. Actually, we propose three techniques based on the measured-based propagations of the radio wave, such as the DOA, direction of arrivals, and then TDOA, time difference of arrival of the signals, and DRSS, differential received signal strengths. But in this case, I will present only DRSS. You can contact me about the DOA and TDOA that we have been proposed. And then, why we choose the DRSS? Actually, there is already available the RSS FG. This has been proposed in Success of Wireless Communications in 2009. DRSS based 4G. This is using monitoring spots. This monitoring spots only for RSS case. For DOA and TDOA case, you do not need to monitoring spots. This monitoring spots is like dummy only in offline. In offline periods, is this monitoring spots send the training signal and measured by sensors. So this monitoring spots like fingerprints or pattern recognitions that store in the database to make the profile. So our technique is based on how close the RSS measurement of the unknown target with the profile. But for the RSS case, this transmit power and incident also must be calibrated or at least same. But for the unknown target emitter, we don't know the transmit power, so we cannot detect the transmit the unknown target by using the RSS. That's why we propose the DRSS. For example, this is the factor graph. The square is factor node or function node, and then or check node, something like that. Factor graph, you have something on something famous for the LTPC for the codings. It can be used for many cases, also for FFT, something like that. But in this case, using the geolocation, and this is variable. So this is from the measurements in samples in what? Yeah, we do not do the measurements. Actually, the real measurement is we already conducted by our partner Codens, now still processes. But in this case, we still use the model test. This is the samples with Gaussians distribution. And then in here, it's called convert to the dB, and then we subtract to the DRSS. This is our purpose, to make the DRSS. And then after that, convert to calculate the mean and variance. After that, this is the main functions, and then some product algorithm to get the x and y. Yeah. This is very simple. We use the linear plane, the linear plane equations to approximate the profile. So, for example, this is from monitoring spot. For example, four monitoring spots near to the target is enough. This is X, Y, P, and C. And this is from measurement. From this measurement, we can predict the X and Y target. But we need to find the coefficient of this one. By using the monitoring spots, we know this value, and this value. By this square, we got this variable, this coefficient. So we know this one, this, and this. Only X and Y is the target. This X and Y from mean and variance we use for the AutoCAD. This is the summary what happened in the each node. The iteration is between this one, because this is point equations, point different equation, we need iteration. So iteration is between this one to get the X and Y until converts. If it's not converts, only two links for example 3 sensors, only two, 1, 2. We combine with some product algorithm and we pass to another automat. But if it's already converts 1, 2, 3, we combine all of the information by using the sum product algorithm. So these equations create this plane. For example, we use in this case it's very simple models, path loss exponent models. We can see that wider the monitoring spots, there is gap. So the estimation of the position is getting worse. But for example, this one 100 meters, there is intersection, so the position detection is better. For example, like this, from 800 meters and until 100 meters, this is the accuracy can be more near the monitoring spot the targets, more accurate. But as I said before, that the RSS case need to know the transmit power. What happens if the transmit power of the unknown target and the monitoring spot is different in 5 dB? In RSS case, there is big gap. That's why this technique cannot reach the target. But in DRSS, there is intersections. So by subtracting to RSS, we eliminate the necessity of the knowledge of the transmit power. So we can reach the targets with better performance, with high performance. We can see from this, why we this is can be seen with this very simple models with path loss. Actually, in our reference, RSS is used for the indoor in the wireless communications transactions. They're using for indoor with shadowing. Which I think they also did the field measurement using the access points for verify the techniques. And the techniques is very good, but we can see for simple models, and also we extend to outdoor case. We can assume this is for free space loss. For example, in this reference they're using for indoor like 6 meter times 6 meters. But in our case it's 200 meter times 200 meter for the monitoring spot area. Yeah, with very simple parallels, we can see that the RSS case cannot detect the unknown radio parameter if the knowledge we don't know the transmit power. But for the DRSS, we can see this very stable after 20 degree SNR. You know, indeed that we need more iteration, about 30 or 40 iterations to make this conference compared to the RSS. So I can conclude that in my presentation that the DRSS and geolocation solve the problem of the previous technique, the conventional technique of the RSS FG that cannot detect the unknown radio emitter, for example, illegal radio. DRSS can detect around 3 meter accuracy with the 200 meter monitoring spot area, and the sensor is around 1 kilometer to 1 kilometer. And then it's offered around 30 iterations. And our proposed technique is still only for the single static illegal radio. So we will take to extend it for multi and moving targets in our future works. Thank you very much for
We have time for questions.
What is the minimum number of monitoring nodes required for? What is the minimum number of monitoring
spots? Monitoring spot.
Monitoring spots.
Sensors.
Yeah. Monitoring spots in this case, in our case is to by using the least square and this equation, this is linear plane. So because this is linear plane, you can see this is used like rectangular. So for monitoring spot is the optimal one.
If you increase the number of monitoring, does the accuracy increase? That is
If we increase, this is still not so much difference because this is still flat. The plane is still flat. But the problem, if we increase the monitoring spot, if the monitoring spot, the additional monitoring spot is far away, it will contribute to worse approximation of this plane. So this is better for and near to the monitoring spot and monitor to the target.
just a quick another one. If you have two unknown, so how do you proceed?
Two multi and moving target for my future works.
Very good answer. Yeah.
Okay, did I understand correctly that you have tested this in indoor environment also?
Yeah, the indoor is in the literature from the transaction of wireless communication 2009 in Huang.
Okay, because I think that there will be huge issues in multipath environment when you can have pretty strong destructive interference or constructive interference. So this kind of panel measurement like measurements may not be reliable.
So in indoor case, the literature is with very small monitoring spot area, they can make the approximation of the shadowing case, shadowing of heading of the measurements. also the instantaneous fadings and this becomes to the samples, and sample is in this case following the Gaussian distribution. This is what I found in the literature for the indoor case. And they make the measurement also in the indoor using the access points.
For indoor, there is a recent paper from MIT, I think like 1 month ago, when they used phase difference on Wi-Fi channels. They jump from one channel to another, and based on the phase at the receiver, they are able to estimate the distance between the sender and the I invite you to look at the paper also. It's quite interesting paper from MIT, and they have great implementation of it. And there is a drone following the guy, staying at 1 meter away, because they are able to estimate the distance very accurately.
So in this case, DRSS become range.
Final question.
Okay. Sorry, I have a related question. So, in your model, you just consider the pathos or the fluctuation due to the multiple tablets asked already previous. Because your performance should be so much dependent on your movements. Yeah. Because you mentioned that this is still the simulation. So I was not so clear which level of the propagation mechanism have been modeled in this study.
What do you mean? The level?
I mean that whether you introduce some kind of the fading fluctuation in your model for the evaluation.
Fading flat.
Yeah.
Actually, this is only pure Atlas exponent.
So what represents this assumption is the question.
Yeah. Actually, this represent for the such as free space loss. And then also this is on, we want to solve very simple models to show that the conventional technique also cannot be used for that.
So now you have the assumption that you have the direct relation between the RSS and the distance.
In this case, we only use the recognition, like the similarity between our equations models with the RSS is stored in the database using the model code. So this is not the
Okay. So you still store the RSS and the database.
Yeah. For the application.
So we have, that final question. Very
Yes,
quick one.
not question, but
Yeah,
just
hold
one
on.
comment.
Yeah, hold on.
Just one comment. He passed his final defense 2 weeks ago, and now we should call him Dr. Aziz. Congratulations.
Thank you for a great comment on that. So let's move to the next speaker. Next paper is channel dynamics and SNR tracking in millimeter wave cellular systems. So it's the first paper on real millimeter waves in our workshop. So we are glad to. You have to go to the USB device.
Will come up the
Here is. Okay, and then
XC.
for macOS. The people for macOS, you can install it and then
Okay, connecting.